Welcome to the course on risk modeling in insurance. This video provides you with a more detailed background on generalized linear models as a regression framework for the analysis of non-normally distributed response variables. You covered a first example of the use of generalized linear models in insurance pricing in the previous videos. In this video, you will get a broader view on the use of GLMs in different aspects of actuarial science. And a standard reference on GLMs in the statistics literature is the book by McCulloch and Nelder. A nice overview paper is the paper by Haberman and Renshaw from 1996, which sketches various applications of GLMs in actuarial science. And these include, among others, rate making with characteristics that can be measured a priori, a posteriori rate making plans, including credibility theory and bonus-malus schemes, loss reserving or claims reserving, and the modeling of mortality data. Now, if you are looking for more detailed references on GLMs and their use in actuarial science, I kindly refer you to the sources mentioned in this sheet. In order to launch a general discussion on generalized linear models, you will start from the following basic premises. You consider a set with independent response variables in the presence of covariates. Characteristic of a GLM is that you will model a transformation of the mean with a linear predictor. In this notation, beta 0 refers to the intercept and p covariates are used in the linear predictor. GLMs allow to include non-normal errors, such as binomial, Poisson, or gamma-distributed errors. And as usual, you will estimate the regression parameters in a generalized linear model with maximum likelihood estimation. Now, as you probably noticed, a peculiar feature of GLMs is the distributional assumption of the response variable, which can go beyond the normal distribution. More specific, any distribution from the exponential family is possible. That is a class of distributions for which the theory of generalized linear models has been developed. A density from this family can be written as follows. And in this notation, theta and phi are parameters, and a, b, and c are functions. Further on in this video, you will learn how some well-known densities can be rewritten into this particular format of a density from a distribution that belongs to the exponential family of distributions. Now, for a density from this family, you will first derive a general expression for its mean and its variance. And hereby you will start from the density as printed on the previous sheet. You will rely on the following result from probability theory. So let L denote the log density and let U denote the derivative of the log density with respect to theta. We approach L and U as random variables. So we know that the expected value of U equals 0, and the variance of U equals its expected value squared, or it is equal to the expected value of the negative of the derivative of U with respect to theta. You will now apply this result in the context of the exponential family. So the log density, in this case, starting from the expression on sheet 5, is given as follows. You will take the derivative of this log density with respect to theta, and that gives you the expression for U. Again, consider it as a random variable. The derivative of U with respect to theta then easily follows. And now we mentioned on the previous sheet that the expected value of U must equal 0. So with the notation mu for the expected value of the response variable y, this implies that mu must equal the derivative of b with respect to theta. And there you see our general expression for the mean of a distribution from the exponential family. Now, for the variance, you will work in a similar way. As mentioned on sheet number 6, the variance of u must equal the negative of the expected value of the derivative of u with respect to theta. You can then use the expression for u and for its derivative as derived on sheet number 7. The expression for the expected value of u prime, the derivative of u, then follows quite easily. Now, combining this expression with the expression printed top of the sheet, you see that the variance of u minus the ratio of the second order derivative of b and the function a evaluated in phi, this must be 0. And to retrieve an expression for the variance of y from this relation, you will calculate the variance of u from its expression as given before on sheet number 7. Putting this all together, you will see a general expression for the variance of y appearing. It is equal to b double prime multiplied with the function a evaluated in phi. So, whereas the variance in a normal regression, in a normal linear regression, is fixed and constant, the variance of a random variable with a distribution from the exponential family is now a product of two functions. So first there is b double prime, and that is a function of theta, and it only depends on theta. Now here you should be aware of the connection between mu, the mean of our random variable of interest, and the parameter theta. In particular, mu equals b prime evaluated in theta. So replacing theta with the inverse of b prime then demonstrates that this function in the expression for the variance of y is a function that depends on the mean. It's called the variance function. So in a GLM, you will be working with a distribution where the variance is a function of the mean. Second, the function a of phi is typically of the form phi divided by w, where w is a weight and phi is the so-called dispersion parameter. It's a constant in the expression for the variance. So, having this as background information, you will now convince yourself that some well-known distributions can be recast in the form of the exponential density as it was given on sheet number 5. Let us start with the normal density, with a mean parameter mu and a variance parameter sigma squared. The usual specification of this density is printed here. You will now rearrange the terms in this expression. First, you put everything inside the exponential function. You work out the square, and you look for a term that is a first power of y multiplied with some parameter. You look for a term that does not depend on y but uses this parameter, that's in this case the mu, and you look for the rest term. So the expression of a density from the exponential family, as it was given before, now uses parameters theta and phi. And in the expression for the normal density, you will choose the theta parameter equal to mu and the phi parameter equal to sigma squared. The function a of phi is then the identical function, and the function b evaluated in theta must equal theta squared divided by 2. The function c, which depends on y and on phi, then contains the rest of your expression here. With these choices, the normal density can be specified in the form of the exponential density as given before. Moreover, as a density from the exponential family as printed before. Moreover, you can convince yourself that the expressions for the mean and the variance, which we derived earlier on sheets 7 and 8, are true. Indeed, the first order derivative of b with respect to theta is theta. And since theta equals mu, you retrieve the mean of the normal distribution. The second order derivative of b with respect to theta is equal to 1. And the function a evaluated in phi is phi, and phi equals sigma squared. So indeed, we also find, starting from our general expression for the variance of a member of the exponential family of distributions, we retrieve, starting from this general expression, we retrieve the well-known expression for the variance of a normal distribution, in this case, the parameter sigma squared. Well, similarly, the probability function of the Poisson distribution can also be written in the form of a density from the exponential family with suitable choices for theta, for phi, and for the functions a, b, and c. And again, you will start from the usual specification of the probability function of a Poisson distribution with parameter mu. You will put all the terms inside the exponential function. You will choose theta equal to log mu, and you will choose phi equal to 1. The choices for the functions a, b, and c, as given on the sheet, then suffice to demonstrate that the Poisson probability function is a member of the exponential family of densities. And once again, you can verify the expressions derived for the mean and for the variance of a distribution from this family of distributions. For example, the mean must equal b prime evaluated in theta. And that is true because the first order derivative of b, that's again the exponential function. And if you take the exponential function evaluated in theta, and you see what the expression is for theta, that's the logarithm of mu, you will get for the mean the exponential of the logarithm of mu, so that's mu. And that's logic because indeed mu is the mean of this Poisson distribution. And you can do a similar reasoning for the variance, right? Sheets number 12 and 13 give you two additional examples which you can verify as an exercise, as a do-it-yourself exercise. So there is the gamma distribution on the one hand and the binomial distribution on the other hand. So you're now ready to process the ingredients or the building blocks of a GLM. Well, consider response variables yi and a p-dimensional vector xi. Here index I denotes the subject of interest and it runs from 1 up to n the sample size. A GLM is then a regression model with 3 building blocks. First, there is the random component. So the random variables yi follow a distribution from the exponential family of distributions. Thus, the normal, but also the Poisson, the gamma, binomial regression, all of that is possible within this GLM setting. Second, the systematic component, or the linear predictor, specifies the explanatory variables x1 up to xp in the model. More specifically, their linear combination in creating the so-called linear predictor. Third, the link function then specifies the link between the random and the systematic component. It says how the expected value of the response relates to the linear predictor of exploratory variables. So these are the 3 things which you should need to identify in order to define the GLM that you will be working on. So you pick a distribution from the exponential family of distributions, you specify a kind of regression structure through the linear predictor, and then you specify a function j such that j evaluated in the mean of your distribution equals the linear predictor for a particular observation under consideration. Now, let's dive a bit deeper into this third building block. That's the link function. So you recall the following connections that hold for GLMs. There is the linear predictor, here denoted with eta. It is a vector x transpose times a vector beta. And the link function j connects this linear predictor with the mean of the distribution, the mean of the response variable. Now, j should be a monotone and differentiable function, and you will see for some specifically chosen GLMs which link functions make sense. Well, first you will consider the setting of normal linear regression. Here, both the mean and the linear predictor take values along the real line. They can be positive or negative. Therefore, a popular choice for the link function with normal linear regression is the identity function, because the mean can take positive and negative values. An alternative is the class of Box-Cox transformations, but those will not be used in this course. Second, in a Poisson regression model, the mean of the distribution has to be positive. Therefore, the function j should map a positive real number, the mean of the Poisson distribution, to a real number, because the link function maps the mean to the linear predictor, and the linear predictor can take positive or negative values if the regression parameters beta are freely estimated, which we would like to have. And therefore, an obvious choice of a function j that does this is the logarithm. Third, in a binomial or a Bernoulli regression, the mean mu is the probability of success, which takes a value between 0 and 1. Thus, the link function j should map a number between 0 and 1 to the real line. And which type of function does this? Well, the inverse of a CDF does exactly this. It takes a probability and maps it to a real number. And therefore, you will use, for the link function in binomial regression, you will use you will use as the link function the inverse of a cumulative distribution function. And two popular choices for this have been proposed in the literature. First, the CDF of the standard logistic distribution, with its inverse printed over here on the sheet. The link function is then called the logit link, and the corresponding regression model is a logistic regression model. And second, let f be the CDF of the standard normal distribution. Then you will use as the link function the inverse of the CDF of the standard normal, and the regression model will then be referred to as a probit regression model. So that concludes our discussion of suitable link functions. So we conclude that it really depends on the kind of distribution, kind of response variable that you're modeling, which type of link function makes sense. Good. Now, to estimate the regression parameters in a GLM, you will use maximum likelihood estimation. This was already demonstrated in the videos covering Poisson regression. In general, you will not be able to solve the maximum likelihood equations analytically, and you will return to numerical methods, such as Newton-Raphson, Fisher scoring. And it turns out that with GLMs, these optimization strategies can be written as a weighted iterative least squares algorithm or strategy. R will do this kind of calculations under the hood when you call the GLM function, and we will not cover the details in this course, but if interested, feel free to check the available background material to see all the details about how this works numerically. So this concludes our first video, which gives you more background, a bit more theoretical background about different types of GLMs that could be interesting in modeling insurance data.